Okay, this is Mr. Anderson for Math 130 Statistics at Kellogg Community College. We're going to start in Chapter 8, the steps of hypothesis testing, the traditional method. And what we're going to do is I have typed in most of the responses to this, and there's going to be some that will be hand-drawn. But today's section is going to be a lot of information about what we do with hypothesis testing and why do we do it. The steps of hypothesis testing is a hypothesis. Now you've been around enough to know that a hypothesis is a guess or some kind of conjecture about what you think may happen in the real life. In your field, whether you go into science or psychology, applied math, or some practical math, you will maybe do some tests and run some tests, and it's going to be important to see if what you're doing in an experiment is having any effect on your population. So hypothesis testing is a decision-making process for evaluating the claims of a population. So we're going to use, this kind of testing to see whether or not something is being changed or something isn't being changed by some kind of action. Because the real question why we do hypothesis testing is you're going to see is the real difference in your averages due to chance, just sampling error. For example, there might be a claim that attendance after spring break does not decrease. In fact, this might be for someone who's advocating for spring break for colleges or institutions, and I'm completely making this up, but let's say someone says, hey, spring break attendance doesn't go down. And if somebody notices that the average attendance changes, maybe that's due to just due to chance or sample error. So we're going to do some hypothesis testing to see, if that's a true claim or not. Now, what's involved in hypothesis testing is to define your population, who are we looking at, state your hypotheses, which is I don't think attendance goes down during after spring break, and the other alternative hypothesis to say, well, it does. We can pick a significance level of 90, 95, or 99%. You're probably not going to want to pick a significance level that's lower than that because then you lose your reliability factor. Then you get your sample of your population, collect the data, perform the calculations, and those calculations will be done in depth in this chapter, and then you're going to reach your conclusion whether your original hypothesis was true or not. Now, a statistical hypothesis is a conjecture about a population parameter, and we're going to be looking primarily at averages. So we're going to be looking to see is our average going to change or not based on some tests. Now, the conjecture is a fancy way of saying guess. Your conjecture can be false if you make a false guess, but that's what you're trying to do. You're trying to put things together to see if there's a change. Now, the null hypothesis is given h sub 0, and there's no difference between a parameter and its specific value. So my null hypothesis is that after spring break, the average number of people attending or gone will be the same. But the alternative hypothesis would be that after spring break, there is a difference between what I'm saying and what is actually going to happen. And we can collect data, before spring break on attendance, and we can then kind of compare it to afterwards. But there are some other examples given in the book, and this talks about the different types of hypotheses and what we're looking at. Because maybe there's a new heart medication, and putting the heartbeats at 82 per minute, we would like that the null hypothesis is that the medication will keep it at 82. And the null hypothesis would be, the alternative hypothesis would be that, well, your heartbeat will change. It will be not 82 anymore. In the car battery life example, you're going to have a battery life of, let's say, 36 months, and we would all like the car battery lives to get better and better. So we're looking for a change in the positive direction. So we want the average car battery life to get better. So our null hypothesis is that what we do is not going to make the battery better, but we would like to see this alternative hypothesis happen. We want it to get better. And then here's an idea. Let's try to lower our heating costs in the wintertime. Well, the null hypothesis puts our average at our baseline at our house is $78 a month. This is not my house. This is from the book. But you would want to see the alternative hypothesis happen where you're going to lower your heating costs. So you want your average to be lower than 78. Now, what's important about all of these alternative hypotheses is that we might get some movement on our heartbeat or car battery or our heating costs. But the question becomes, is that enough? Like if we see 82 beats per minute go to 85, was that significant? Or if we see the battery life go from 36 to 38 months, is that significant? I know 2 months would be great, but is it statistically significant to say that we're doing good jobs here? And after you caulk your windows and insulate and maybe put a plastic over your windows, if your heating bill goes down to $70, is that enough, or was that basically a sample error? So we have to do some tests. Now, when we're looking for a change just away from an average, we call this a two-tailed test, where we're looking at basically we have an average and we want to get essentially something that isn't. A right-tailed test is in the car battery life problem. And the car battery life problem, I'll do a quick picture of it here. If we have an average of 36, this is going to be our mu here, 0 standard deviations away from our norm. But if we have 36 months of 36 months of battery life, we would like to see that kind of go towards this right tail over here. So we're kind of looking for a right-tailed test. And for the heating costs here, again, we have a 0 standard deviations away from the average, which is $78. But what we would like to do is we'd like to have our we would like to see our average somewhere over here towards the left tail. So that's why we call it a left-tailed test. All right, so back to the worksheet here. Going to give some more information before we talk about these specific tailed tests in either direction. We're going to talk about a statistical test. Now, statistical tests use data from the sample to help accept or reject the null hypothesis. Now, the null hypothesis can be one of two things, because either your null hypothesis is going to be true, so let's put H sub 0, because we're going to either have the null hypothesis true or the null hypothesis is going to be false. All right, now let's make a 4 square little chart right here. So let's say, for example, that I'm going to say that attendance doesn't change after spring break. Well, if that's true, but you reject that answer, you've made a mistake. You've made something called a type 1 error. And 1 is a numerical 1. And that's when you reject the null hypothesis when it's true. Let's say I was a big, proponent saying that, oh man, the attendance is going to change after spring break. But if we run the data and you find out that that's the conjecture that, hey, attendance doesn't change after spring break, and then I reject that, I've made a type 1 error. What I should have done is I should have accepted the fact that this was true. Now the book will put down not reject, which is a fancy way of saying to accept. So what I should have done is I should have not rejected that null hypothesis. The null hypothesis was students will have the same attendance before and after spring break. I should have not rejected that, but if I do rejected it, I make a type 1 error. Now, type 1 errors are easy to measure. What's tough to measure is this error. Let's say that was a false conjecture. Like I said, oh man, attendance doesn't change after spring break. Well, what if it what if it did change significantly after spring break? Then I should reject it. But if I stick to my guns and say, oh, I think I think that I still think I'm right. I still think attendance doesn't change, and the data overwhelmingly says, oh, the attendance is changing, then I made a type 2 error. And type 2 error is when you don't reject the hypothesis when it's false. So I'm basically sticking to my guns saying, oh man, attendance doesn't change at all, but it does. I don't reject the original assumption, and these are harder to statistically prove. So we're going to spend most of our time working with our type 1 errors because we can work with something called a level of significance. See, we want to find differences between the null hypothesis and the hypothesized average, but how much of a difference is needed to do so? Because the thing is that what if I do find that there is an attendance change after spring break? Then I should say, oh wow, then it's false. Well, wait a second, maybe that change after spring break wasn't significant enough to me to throw out the idea that the population changes significantly after spring break. So we got to talk about something called a level of significance. The level of significance is the maximum probability of committing a type 1 error. And it's also called alpha. So the maximum probability of committing a type 1 error is alpha. So we're either going to deal with a 10% significance level, a 5% significance level, or a 1% significance level, which means that I want to be a 10% chance of getting this wrong, a 5% chance of getting this wrong, or a 1% chance of getting this wrong. Now, obviously, you might think, well, shoot for that one. Yeah, but that also might mean that we would need some pretty hard data to show that that's true. If I work with a 10% level of significance, then I've got a 90% chance of getting it right and a 10% chance of getting it wrong. All right, I'm going to let you pause this now and copy this down. I'm going to move this clicker down here. Whoop. Okay, so we have to set up the idea that we have to be within a 10% chance of getting this wrong, a 5% chance of getting this wrong, or 1% chance of getting this wrong. And that is going to make something called the critical value. The critical value separates the critical region from the non-critical region. So the CV, that critical value, is going to be very important because that's going to be our border. Everything to one side of the critical value is going to be not significant. Everything to the other side of the critical value is going to be significant. For example, if we have a two-tailed test, our critical values are going to separate this region. Our CV is going to be here, and our CV is going to be here. So everything over here is going to be, hey, that's significant, and everything over here is going to be significant. So this is an example of a two-tailed test. The critical values will be bordering these positions. Now, if you have a right-tailed test, your critical value would be here. And if you had a left-tailed test, your critical value would be here. I would write that underneath, but I ran out of room. Now, the critical region is the range that the indicated significant difference, is the range that the indicated significant, I think I typed this wrong, that indicates, sorry, one letter wrong changes the whole thing there. It's the range that indicates a significant difference, and then we should reject the null hypothesis. So if we find that our tested average is inside any of these shaded zones, the null hypothesis is false, and we should reject it. Now, let's see here. We also have the range. This is the non-critical or non-rejection region, is the huge span in the center that indicates the test value, well, was probably due to chance, and we should not reject the null hypothesis. So if your average is anywhere inside of these non-shaded zones, then you probably don't have your null hypothesis is okay, and you don't have that. Now, see, in most cases, we want to reject the null hypothesis. Now that's now obviously just because of maybe you want to see a change. You really want to try to reject the null hypothesis and show that the H1 is true. So this is really what we're wanting is in that square up above. We want the null hypothesis to be false, and then we want to reject the null hypothesis, and that will be a good thing. That is true. We've made the correct assumption. Our original idea was wrong. We maybe applied something, like let's say we applied a drug or maybe a new thing to our battery, and wow, we can now say that we've improved our battery, we've improved the drug, or we've lowered our heating costs, so we're rejecting our original null hypothesis, which is great because we've made some difference. Now let's take a look at the only math that's actually in this chapter here, which talks about looking at left tail, right tail, and two-tailed test before we get to the homework, which is on page 412, 1 through 13 all. So let's look at the left tail test. The left tail test here is going to be, first of all, let's draw a normal curve. All right. Now our mean, median, and mode is in the middle, but we're looking at means here, which is 0 standard deviations away from the norm. So when we do a left tail test, we're looking at this shaded region on the left-hand side. And what we're hoping is after we get done with the test, we're hoping that our mu is inside of the shaded zone. So we're either going to pick an alpha or a tail of 10%, a tail of 5%, or a tail of 1%. Now what I'd like you to do is I'd like you to go to the table, the Z table on the inside flap of your book, and look for where our 10% is. Now you'll find that your critical value there, according to your Z table, is going to be negative 1.28 standard deviations away from the norm. So if you get an average that's negative 1.2 standard deviations away from the norm, then you have your critical value, and your null hypothesis should be thrown out. Now if you look at 0.0500, then you'll notice your critical value is negative 1.65. Now I'd like you to go and look for this one in your book, pause the video, and then come back and see if your critical value is right. The critical value of a 1% is going to be 2.33 standard deviations below the norm. So if you want to get a 99% confidence rate or a 1% level of significance, you want to make sure that your new average is way far away from the norm, and that's pretty tough to get. You'd have to do a lot of science or a lot of research or implementation to find out that something was that far away from the norm. Now the right tail test, again, please copy this down because this is going to be pretty important. After I shift this, it's going to go away here. Okay. So the right tail test, let's see, can I fit the right tail and the two tail? No, not necessarily. Okay, the right tail test here, oops, get my pen back on the screen. Okay. The right tail test is going to be where we want the shaded area to the right. Again, this is my 0 standard deviations away from my average mu. Now in here, we're going to have our same alphas, which is 10%, 5%, and 1%. So 0.10, 0.05, and 0.01, or 1/100th, 5/100ths, and 10/100ths, or a tenth. Now you'll notice that the critical values are now going to be on the right side. Well, to do that, all you need to do is take your values from up above, and since this is a symmetric normal curve, you'll notice that these are all positive. 1.28 standard deviations from the norm, 1.65 standard deviations away from the norm, or 2.33 standard deviations away from the norm. Pretty straightforward. You can see that the left side and right side would be symmetric. So if your new car battery length or life is inside of the shaded zone, either 1.28, 1.65, or 2.33, you can be 90%, 95%, or 99% certain that you didn't make a mistake. Now in the two-tailed test, again, I'll let you copy this down, and as I scroll this, yep. Okay. Oops, there we go. Here we have now our two-tailed test. Is going to be a little bit like the last chapter that we dealt with, because some of you went to go find your Z table, your values on the Z table there. You maybe made a mistake because when you looked for, your 90% confidence interval, you looked at, 0.90 and 0.10, but that's not right, because when you look at these for an alpha of 10%, 5%, and 1%, this isn't 0.90. This is technically 0.9500, and this is technically 0.0500, because this is a two-tailed test, so you got to take your alpha and divide it by 2. Very important to take your alpha and divide it by 2 to find these scores. So this is going to be, the critical value is going to be plus or minus from the top and bottom 1.65. Now I want you to pause the video and I want you to try to find the critical value of a 5% tail, which means 2.5% in either one, and go look on your Z table to find it. Alright, now, you should not have looked at 95% and 5% for your 5% right there. You should have looked at 0.9750 or 0.0250, and the closest Z table to that is going to be 1.96. You'll always round up if you have the choice between going with one or the other. And now pause the video and try this one on for size. Try to find your critical value. Alright, you should be looking for not 99, you should be looking at 0.9950 and 0.0050, and that critical value is going to be plus or minus 2.58. Alright, great job with that. If you have any questions, please email me.